Hello everyone, my name is Jeroen van der Hoofd and I'm a postdoc at Kent University. Today I would like to present to you work we did with colleagues from Klagenfurt University and Osijek University on objective and subjective evaluation of the quality of experience for point cloud streaming. Does anyone remember how Princess Leia was presented here in this Star Wars scene? Well, I would say they are, because this is one of the very iconic scenes where, for the first time in cinematic history, the concept of 6 degrees of freedom was introduced. Why? Well, this hologram could in fact be watched from multiple angles. In different shots, Princess Leia was represented from a different view. And if you think about 6 degrees of freedom, we want to be able to move our head, we want to be able to move our body, then this comes very close to it. Now, since then, 40 years later, a lot of advancements have been made, and we're getting closer and closer to holographic type communication, or HTC in short. Dynamic scenes require a significant amount of data. The objects that you see here, they are not regular video content. They are objects that were really captured and modeled in 3D using a point cloud representation. Now, a point cloud you can actually just see as a huge collection of points, each having an XYZ coordinate, so the geometry of the object, and for instance RGB or YUV values to represent the color of the object. Now, having 1 million points together takes a lot of data, and especially if you're working with different frames and if you want to have moving objects as you just observed here. Indeed, this dataset requires between 3.8 and 5.7 gigabits per second to stream. And that would mean if we combine these objects together in one scene, it would require approximately 20 gigabits per second in order to stream it. And of course, that's really a lot. Recent advancements have made it possible to compress this, to compress point cloud objects. If we have a look here at the soldier object using the MPEG reference encoder, which was proposed 2 years ago, then we can actually see that we can reduce the amount of data needed by a factor 100 without really impeding the visual quality. If we go even further, reduce it by a factor of 1000, then we do see artifacts, we see these blurry effects and low video quality. But it is possible to recreate different versions of quality for these different objects. And that means that we can use adaptive streaming. Now, adaptive streaming, how it usually works is we take a video, we split it up in segments of, for instance, 2 seconds, and we encode it using different quality representations. And then at the client side, we can simply stream the content and we can download these fragments one by one, adapting it to the available bandwidth in the network, for instance. Now with the point cloud objects, if you think about it, we have multiple objects, we bring them together in one scene. What we could do is we could add an additional dimension, the object dimension, and we could download or stream these different objects at different quality representations, depending on what region of the scene the user is looking at, which just makes it possible to use HP adaptive streaming in this use case as well. In this work, we had 2 main research questions that arose when we were working on the previous paper, on the previous study. First, we were wondering what the impact is of the network and content characteristics on the perceived video quality. How does the user perceive this? Are there differences, for instance, when if a user changes the field of view, so changes the focus from one object to another, are there quality discrepancies, etc. Second, how do objective metrics, image-based metrics such as PSNR or SSIM, how do they correlate with the subjective ratings for the perceived video quality? Those are the 2 main research questions that we address in this work. Now, to address these challenges, of course, we need a methodology. Now, what we did was we used our setup from previous work where we had really an adaptive streaming framework, and we generated multiple scenes. For instance, those were computer-generated traces where, for instance, a user is walking in a line parallel to the different objects, or a scene where a user is focusing on this particular object, zooms in, and then zooms back out. Only then later to change the focus to another object. And then quite similar here for the soldier object, which has a lot more texture and a lot more color. Zoom in on the soldier object, zoom back out, shift the focus and do the same again. So 3 scenes, 3 sequences that we generated. And for each of these scenes, for each of these videos, we provided 8 configurations for subjective evaluation. One parameter is bandwidth, so the amount of bandwidth that we have available in the network. We have the allocation, so the way in which the bandwidth is allocated to the objects. If you have a scene with 4 objects, you could focus first on the visible objects, so increase the quality when possible, and only then focus on the non-visible objects, but you could also do it in a more uniform way. And then finally, we have prediction, which means that we buffer content for the future using either the most recent position, or we use the perfect knowledge that we have of the future in order to buffer the content that is visible at that point in time. In this work, we use 3 configurations for the bandwidth, so 20, 60, and 100 megabits per second. And for the allocation, first focus only on visible objects without prediction. So use the most recent information on where the user is looking at this point. Then also with prediction. So assuming that we know perfectly well where the user is going to look at in the near future, and use the rate adaptation algorithms to select the appropriate quality based on that. And then also allocation on all objects, so that means uniform allocation. So first we will increase the quality by 1 for all of the objects, and then only go to the next quality representation. And finally, a scenario in which we have unlimited bandwidth, where we use the uncompressed content as a baseline and to compare as well these results. To give you an example, this is what the video looks like at 20 megabit per second. You can actually very clearly see the low quality, especially when switching. When you zoom in on the woman here, you will see that texture gets a bit lost and there are some artifacts visible in the video. This is just one of the videos. Now, participants were asked to rate the video quality. We use a single stimulus study, which is quite different from double stimulus studies that you see most of the time. It was interesting for us to know whether or not these subjective testings evaluations work without the presence of a ground truth, right? So the user was put in front of the screen and had access to a laptop where we asked to rate based on ACR, so on a continuous scale from 0 to 100, what the quality of the video is. Then on to the results. So for the first research question, the impact of network and content characteristics and also system characteristics, such as the presence of prediction or no prediction. I will not show all the graphs here. I really want to refer to the paper for that, but we have 2 CDFs here, where we show the mean opinion score on the x-axis and the CDF on the y-axis. And we can actually see that studies can distinguish between the different bit rates quite accurately. If you look at 2016 100 megabit per second, there are clear differences here, smaller differences between 60 and 100, because the impact of having higher bandwidth is less clear here, but with a very clear also increase when we have no compression. Right? Furthermore, we had a look, for instance, at videos with or without viewport prediction, and we can actually see that there's a clear improvement here, which means that if we can predict the movement of the user and predict where the user is going to look at next, we can actually increase the video quality as perceived by the end user. Second research question dealt with how do objective metrics correlate with the subjective ratings, and here again we can see some clear results. There's a clear correlation between objective metrics and the mean opinion scores. As you can see here for the PSNR, but also for the SSIM and for the VQM scores, there usually is a linear correlation between the mean opinion score for one configuration of videos and the objective values and objective metrics, the values for that that we observed. We calculated the correlation using Pearson and Spearman rating, and here we observe that SSIM actually reflects best how the user perceived the video subjectively. However, part of the model is still explained by the selected source, by the selected content, which means that there are differences. This is for SSIM, but this is also true for VQM, based on the content. So the mean opinion score alone is not enough to predict the objective metric, or more importantly, the other way around. If we have the objective metrics, the VKM, the PSNR, we cannot accurately predict the mean opinion score without knowing what content we're looking at. So to conclude this brief talk, we got consistent responses without the presence of ground truth, which is good. We have single stimulus studies and those work. With regard to our first research question, the impact of network and content heuristics is clear. It is explainable. And with regard to the second research question, we can see that there's a high correlation between objective and subjective metrics, but the values need to be adjusted to the considered content. And thus, there's a need for more representative metrics and QoE models. With that, I would like to thank you for your attention, and if there are any questions, please feel free to ask them.